All right, so let's go with our slides. Okay, this is our chapter 3, and let's make a recall back before we go on with the reductance here. Okay, so the previous one we will learn about the magnetic field, how is it works, okay, especially based on the magnetic field where we have the south north, which we have the south pole, which we call as a north pole. At the same time, we also learn about the formulas. Okay, most of the things that based on our capacitance, based on the magnetic field, we still have a theory, but our theory is maybe I can say maybe from 20% to 30%, but most of the thing will be covered up is based on your calculations. So when we go through based on the slides, okay, most of the slides, okay, we have a formula. So I want you to jot down based on the formulas, okay. So the one we have learned before this based on your magnetomotive force, which we use the equations of F based on the F equal to Ni ampere. Okay, as we know, we have N stand for numbers of inductors. At the same time, based on the current, is current based on the current flow into the inductor. Okay, when they say it's based on the conductor or based on the turns, which is indirectly is related to your inductor. Okay, but since magnetic field and also inductors are related. Okay, so that's why no choices, we need to go on with the magnetic field, then only we can cover up with the inductor. So when they say numbers of a conductor, or even though they say based on the turns, okay, it means it's based on your usually based on the any materials, okay, which we allowed it to flow the currents, or we say as a material, or we say as a copper. Okay, but not necessarily all the coils is built out from the copper. They have different materials which we call as a semiconductor, right? So this the one they call as a turn. Okay, so this turn, this the one we say as an inductor, and this inductor the one we call as a component. Okay, so this one we go on with the next chapter. All right, so this is the one formulas based on the motive force, which we equal to N times with the I, which is stand for the ampere. Okay, and the next one is based on the magnetic field strength. Okay, this is just a recall back, okay, where we have one more equations where we substitute based on the, not substitute, it's just defined it based on the magnetism force. What is it they mean? And where the point here, you need to take note based on the numbers of the turns. At the same time, you need to take note based on the current flow into the turns. At the same time, you also need to take note based on the length. Okay, so the one they call here, okay, the symbol is actually for the length. Okay, and where at the same time, they try to not match, but they try to show to you MMF equal to Ni. At the same time, they also can define that, which we call as a magnetic field strength times with the current. Okay, so when maybe you can go through some of the reference book, the way, not the way, the methods they write the equation, they have a different method. Okay, but the first one, they always have the basic equation. From the basic equation, they come up with a few steps of the equations. Okay, so when you have many types of the equation, you need to know which equations that you need to substitute for the questions. That's why the equation, they have a multiple equations, but some they maybe don't have the turn, some they only not substitute based on the magnetic field strength. So it depends on the equations, but most of the thing you just take note based on the basic equations. Okay, so the next one, I think we did some example, and okay, so based on the example means not going to touch here. I think in the last class we did a few example. Okay, so I think I also leave it to you with the homework, but Miss can't remember right now. Okay, so let's go on with our chapters today. Okay, so in our chapter, just have a look. So we call as a reductance S. Okay, it's not sensitive. Sometimes when you go through some of the reference book, or even though you find out based on the online source, okay, they use the word S, the capital S for sensitive. Okay, but this one for our subject, okay, for our EEP, inductors, they also represent as S. Okay, at the same time, they also call, can define it as RM. Okay, RM means not ringgit Malaysia, is where we have the capital R and the small m. Okay, it's where we call as a magnetic resistance. Okay. Is where of a magnetic circuit to the presence of magnetic flux. Okay, this is the one they relate with the reductance. Okay, take note, reductance usually means give you, sometimes to find a reductance, you need to have some magnetic field strength, or you need to have some magnetic calculations based on the force to achieve, not to achieve, to get the last answers for your reductance. But usually they come up with a basic concept, okay, basic equations where it can be stand in this way. Okay, let's have a look. You may see they have, okay, I just let you know, this we call as a first part, this we call as a second part, this we call as a third part, this we call, okay, the next on continue, okay, until we have the last part here. Actually, each equation start from here, the first until the end here, actually each of the equations are represent for reductance. It means stand for S, okay, and the way they using the equations, okay, the way they change the equations, you can see. Okay, so you have the MF, okay, it's based on the force, okay, motive force, divide like a theta. It's actually as a flux part, okay, and equal to Ni, they should see like in terms of theta. So when we do go some calculation, then you know how to relate with the equations. So by me explaining to you the theory, maybe some of you maybe know that is, okay, that is the formula for reductance, but you will understand when you start to do a practice, okay. And the next one, you can see the next equation, they shows you based on the HI divided by the BA. So when I ask BA, you need to answer right now. You know what is it B stand for, what is the A stand for, okay? So the next one based on the, okay, these are the symbols of length. Length, at the same time, they're using B divided by the H, okay? This is strength, times with the A. At the same time, they're using a one more equation. Okay, these equations where you can see they're using like a primitivity, okay, there where they have the absolute and also relative. At the same time, they shows in terms of the area. Okay, so take note when they ask you to find reductance. Okay, reductance is take note is based on the of a magnetic field to the present of the magnetic flux. So it's related to your magnetic circuit and also to present the flux. So they want to have the flux in your circuit. All right. Before Miss forget, I just want to let you know. Okay, better for you to write this equation. Those having your notes with you, okay, this using a tab or those using a notebook, okay, write these equations. Okay, so each equation are related, which at the end they represent inductance. Okay, those have notes, maybe just write down. Take your time and write down. Look messy. Let me. Okay, I hope you're already done. Okay, so let's go. So they have a unit for inductance where it's a 1 over h, or represent h minus 1, power minus 1. Okay, or they also have a slash with the WB. So WB, you need to know what is it, Weber. Okay, so these are one are the unit they're using for the reductance unit. All right, so let's go on with the next part here. Okay, next part, they direct to the calculations part. Okay, we'll have a look on this part here. Okay, so I have a message from one of your friends. Ma'am, can we have to use all the formulas or only a final formulas we have to use? You need to understand all the equations. Okay, for your own good, Miss asks you to remember, understand all the equations. Okay, don't understand only one equations, understand all the equations. Okay, so let's go on one of our examples that we have here. Okay. This is the basic one. So in terms of your example, this shows you have the flux here, not a flux, they shows you have like a square, okay, where they're using a materials, okay, because sometimes they can represent as iron, they have a few materials, okay. At the same time, okay, let's go on with the point they're given to you here right now. So inductance of the magnetic circuit, okay, where they defined it, the value is 10 for this one, 12 times 10 power of 4, okay, where you're using the unit AT slash WB. And what the flux in the circuit. Okay, so the things that we need to find, remember sometimes your questions can be short, very direct to the point, sometimes it's a bit longer questions, but sometimes they give you some hidden. Okay, so most of the thing when you start to do any questions, take note the key point first. Okay, so in our questions right now, they ask us to find the flux in the circuit. Okay, so we need to know what the flux is it, the value is it. Okay, so in the same time, they already defined it for us. Okay, have a look on the figure. Even though they not write for us 0.5 is an ampere or how many turns they have, they put some information at the image. Okay, this kind of a question, some information you can find at the diagram, at the sum of the informations you can find at the sentence. Okay, sometimes they're not going to provide for you any diagram, any circuit or any diagrams, but they highlighted to you, excuse me, they highlighted to you directly the informations, okay, in the sentence. Okay, so at this point they can you may have a look here, we can have a look here where we have 0.5 ampere. Okay, ampere means the current flow, okay, into your coil, and also they shows you based on the directions. Okay, at the same time you may have a look, they shows you in terms of the turn, how many turns that you have. Actually this the one, even though they just simply put, okay, from how to say, from miscalculations, so you can have 1, 2, 3, 4. You have 4 example. By in terms of the turns, they already highlighted to you. They have 300 turns, so they can't exactly shows to you the turns is 300, but the only specific for us is 300. So we just assume that we can see the 300 turns here. Okay. At the same time, they're using a flux here based on the theta symbols here. Okay, let's go with the equation that you need to be calculate. Okay, so in term, okay, even you already have the solutions here, right? So in terms of the solution they're given to you, okay, excuse me. Okay, you're going to find the equation at the, excuse me. Okay, at this time, you have the equation that you need to calculate. So the way they calculated based on the turn with the current, okay, you're going to find the force part here. Okay, so let's say I just want to go back to the previous slide. Just have a look. We just want to go back to the previous slide. Just have a look on the formulas here. Okay, just have a look. Okay, this is the way how they related based on the Fm equal to Ni. Okay, I just go back to one more slides here. Let's have a look on this equation. Excuse me. You have Fm equal to Ni ampere, right? This is the one. This is the formula that you need to find based on the force. That's the reasons when you go through the examples here. Okay, at the same time they're using this one. Okay, but this one they have denominator which they call as like a theta flux here equal to Ni. So we're going to take on this part, F equal to Ni. Okay. So that's why we have this one based on the force. Even though not without relating to your reductance, we also can find based on your force, okay, the magnetic force, how you calculate it. So based on that, we can see Ni equal 300 times 0.5 ampere. So this is referred to the turns. This is referred to 0.5 based on your current, and we get the value of the force here. At the same time, have a look the way they calculated based on the flux. Okay, the symbols of theta. Okay, where they're using the force over with the reductance. Actually, these formulas are the same actually based on your Fm. Just now we have F, okay, force, which is an I, and where they're using a theta, if you see the previous slides, where they're using the flux. So they just play your maths. I think all the students here are very smart with the maths, right? So they just bring up the flux at the next direction, then they just substitute based on your calculation. So at this point, you can see they take based on the force. It means this force. Okay, example, this I'm going to put as a R. Okay, just as a reductance, or we call as S. Okay, let me write properly here. Okay, Fm equal to the flux. Okay, at the same time, Ni equal to, okay, this is a flux. I hope you can see the symbols here. So at this point, we need to find this one. So when we want to find this one, of course, you already know Fm is means the force divided by the R. So we can get the flux. It's the same concept they implemented here. So you just substitute based on the equation 150. Okay, then you divide by 100, divide by 12 times 100, 10 power of 4. You get the last answer based on your flux, and the units of your flux is the WB. So this is the way how you need to take note based on the equations. So if you can understand the equations in any way, make sure no matter what the questions, maybe in the tutorial, whatever question is given to you, okay, you still can answer as long you understand the concept based on the equations. Okay, so go on with the next part here. Okay, in the next part, okay, in the next part, they shows you in terms of some example, but they already specific for you the answer. Okay, maybe Miss going to choose for you, not maybe, I'm going to choose a few calculations example from your slides. Okay, maybe not everything, but some I already write as a homework. Let's see here. Okay, some of the slides Miss already wrote as a homework. Okay, so I want you to do it as a homework, but before that, Not right now, okay, later on also you can do. I just want to go on with the sum of them related to your reductance here. Give me 1 minute. Okay, those have OneNote, you may have a look on your OneNote. Oh, this is the last class, okay. Okay, so you just have a look OneNote. Okay, it's similar like your slides, but maybe some of the value mischange, okay? A coil of 300, okay. Oh, this is the next one slide, okay. Okay, just have a look. Maybe you can see some difference in your OneNote and something, maybe based on the parameters value maybe change, okay? But the concept are the same concept. Okay, so now right now just have a look on your OneNote. Okay, so in a OneNote, okay, let me read for you. Okay, I'm just going to take out based on the key point that we have here. So in terms of the first part here, even slide number 33, you may have a look on your slide if you want to have a look on your slides. Okay, a coil of 300 turns, okay, is wound uniform on a ring, okay, non-magnetic material. Okay, the key point that we're going to take right now is based on the 300 turns. Based on this one, 300 turns, okay. At the same time, this shows you in terms of the ring have means a circular reference of 40 cm. Okay, when they highlighted to you a circular reference of 40 cm, it means it's related to your length. Okay, length. Okay, so and a uniform cross sections of 4 cm power of 2. Okay, at the same time, they already specific for you the area of the circular. Okay, and if the current in the if the current in the coil is 5 ampere. So they already specific for us a current. So you just take note the one that you need to have a take note. So at the side here, I'm going to write here. So let's have a look. So I'm going to put N as a turn, 300 turns. They already given for us the Edens, which is 300 turns. Okay, just a symbol of the N. Okay, the next one they also highlighted for us non-magnetic material. Why sometimes when they specific for you a material, so that's the time that you need to take note based on the value of the materials. Okay, so magnetic usually they try to keep based on the non-magnetic material. Okay, but not necessarily every time. Okay, so the ring at the same time they already let you know based on the length. So length means this one. Okay, not liter but the symbols like a L, this L. So you have 40 cm. At the same time you already have the cross area. So the cross area which is stand for your A, okay, which is stand for 4 cm power of 2. So and the next one, they also give us the Edens, which is based on the current. So this current based on the 5 ampere. So you have 4 point there. So A, B, C with the D. So from here you can start to do your calculations here. Okay, so the first one, they ask you based on the magnetic field strength. Okay, it's based on the strength. So when they ask you based on the strength, faster you highlighted the symbols. So easy for you to identify which equation that you need to substitute. Okay, so it depends on you. Maybe you have a different way, all right? So, but most of the thing when you know, just specific earlier what the equation that you need to substitute, all right? And the next one is based on the flux density. So flux density means it's going to represent as a B. Okay, take note, we also have a flux, magnetic flux, and also same time we have a flux density. Be careful with these two sentences here. Okay, and the next one is based on the total. So total means is based on your overall of your total magnetic flux in the ring. So they're going to find in terms of the ring. So this is the some sketch that Miss draw here. Okay, maybe look messy, but look like a ring. This is the one Miss want to point. Just think about it. You have like a, in terms of the circle, like a ring circle. Okay, and you have the coil, and each of the coil you have 300 turns. Okay, at the same time the currents flow into the turns, okay, based on the coils, which is stand for 5 ampere. Okay, so the first one we're going to calculate. So the first one we're going to calculate, we need to define what the equations that we're going to use. Okay, based on these equations, we go on with these equations. Okay, so you may have a look. Okay, so this is the equation that you're going to have. So based on your n over I, okay, n multiple with the I divided by the length. So from there you can have a look. But take note, sometimes you need to use different equation. Okay, so since of your question, they already given to you the turns, they already given to you the current, they already given to you the length. So easy for you to substitute, but not necessarily every time you have all the information. Okay, sometimes they trick you in a different way. Okay, where maybe they ask you to find the length of the circle. Okay, so sometimes maybe they ask you to find the currents, how much is it? Okay, so that's the time you need to relate with the other equations. So now they are already direct to the point where we just substitute the value. 300 times with 5 ampere divided by the length, which is 10 for 40. 10 minus 2, because it's a cm, we change it to a meter. 40 cm. Okay, so you have this one, 40 cm, where we have 40 power of minus 2 meter. So this is the one represented here. Okay, so once you calculate it, you get the value, which is 370.50. Okay, so may have a look. Okay, maybe Miss not sure whether the unit, the same unit or not. Okay, since 40 cm, 304 cm. Okay, the same information that Miss used in the one note. So you will have 3,750 a over meter based on your calculation spot. So the same one you will get based on your calculation spot. Okay, next go with the next part here. In the next part, we have a flood density. So flood density, we use the equation. So you need to know which equations that you need to use based on your flood density. So the next equations is where we're going to use these equations. And how to get this equation? Actually, the one we shows you in the earlier of your slides, where we have the equation that we need to substitute. Okay, just behold, I shows you the back, the equations here. Excuse me. These equations, how they related back, okay, because we have the primitivity on this concept, so they just substitute the value to define the value. So at this point, we're going to have this equation. Actually, they will write in this way. They write as a flux, okay, density flux. You have the absolute primitivity, at the same time you have the relative, then they add at the age. Okay, so in terms of that, the way very specific. At a point, they're not specific any measure, what type of the measure, what type of the relative measure they're going to have in this question. So in this part, we just they just say as a non-magnetic. So we're not going to have any specific value for the material. So at this part, we just ignore on this one. Okay, not every time, it depends. Okay, so once you have, okay, one, you can define your absolute value. Take note, absolute value is always a constant value. We say as a fixed value. Okay, so this is a fixed value. 4 pi times with 10 minus 7 times with 3,750. So you multiple, as usual, you go, once you calculate it, you get 4.712 mt. So m means stand for your milli, t stand for your unit. Okay, your flux, have a look back your flux calculations, how you calculated. Okay, once you done that, you go on with the next one. Okay, the next one, they ask you to find the total magnetic flux in the ring. Okay, so they not ask for the flood density, but this time they want to find based on the magnetic flux. So the way they calculated, they use the equations. Okay, as usual, this equation is a basic equation. If you still remember the way they calculated, have a look. This is actually the one we learned before. Okay, where we have this one. Okay, flux. Magnetic flux. B equal to your theta's density flux equal to your magnetic flux. Magnetic flux. This is the flux density. This is the area. So in your questions, what you did for your your B, you already have the answers for this part. Okay, flood density is how much. At the same time, in your question, they already provided to you the area. So the area they given to you, okay, the area they given to you is this one, 4 cm power of 2. Okay, so once you have the value, you can substitute directly. So it means this value, substitute directly, okay, density flux times with the area, you get the last answer, okay, which is stand for 1.885 micro WB. This is based on a magnetic flux, okay. At the same time, I just want to specify for you again, Miss always repeated a few times, okay. Even for your micro, if you give me the answers in my -6, is still accepted, okay, but it's better for you to use the unit, okay, micro, because that's the reasons we have in your unit, scientific units, okay. So the next one, just see whether I have other example or not, which is related to this one. Let's go on with a few examples here. Okay, this is one more. Should have one more. Okay, slide 34, all right. Let me check one more time, slide 34. Find the magnetic field strength and the magnetic motive force needed to produce. Okay, where we have 0.333 for the flood density. Okay, it is the same thing. Yeah, it's the same thing. Okay, but the things is the value of your the givens here in a one note is a different, not the same, because in your slide they already write for you is 0.33 and the next one is 12. Okay, but the concept are the same. So just have a look on this one here. Okay, so determine the magnetic field strength, okay, N, okay, it means the symbols of the N, the MMF, so it means based on the force requested to produce a flood density, okay, of 0.25 T. So they already given to you a key point here, okay, or we say as a hidden here, based on the flood density. At the same time, they say in the hair gap, okay, for the length is 12 millimeter. Okay, Miss repeat back, the information they given to you for us is based on the flood density, which is 0.25 T, and also just take note based on the hair gap. At the same time, the length is 12 millimeter. So the way we're going to calculate, the first thing they ask us to define based on the magnetic field strength. Okay, so this is the first one. And the second one, they ask you to find the force, motive force. So take note based on the way we're going to calculate it here. So in terms of that, they already highlighted to us, they're not specific for us any material, but they just let us know it's based on the air gap. So when they say air gap, usually free space or they say vacuum, or they say as a hair, the units for your relative always stand for 1. Okay, usually would be stand for 1. All right. So the first one we're going to calculate, just have a look on the way they calculated this one. So the first one, they have a magnetic field strength. Okay, of course we know the symbol is H. Okay, now we just take note based on the equation. So based on the equations where we get based on the flux density divided by the value of your permittivity. But this permittivity where we come up with the concept of this one. Okay, in the next slide you will have that. The way they relate based on the B with the H. Okay, this value, this formula, just take note. Okay, the way they calculated. Remember, this actually represent B equal to absolute with the permittivity with the H. Okay, but in terms of your 1, maybe we can substitute, because any value when you calculate, example we say is 5 pi. Example, just for example, this is a fixed value. Okay, 4 pi times with 10 power of minus 7. Okay, so example I said 5 pi times with the 1, any value times with the 1, we get the same value, the self value back. Okay, the same concept. That's why in this part, shows you based on the relative. If you want to add, no problem, you just add. Okay, you want to show me step by step, please go on with that. Okay, just add, no problem with that. So when you substitute the value 0.25, example, I just put here times 1. Okay, you can take note based on this part. Okay, at the end 0.25 divided by 4 pi times 10 power of minus 7, you get this value. Okay, under 198,400 940 per meter. Okay, this is based on your unit. This unit A, okay, divided by the M based on your unit here. So once you're done, you get the last answers here. All right. So this is based on the magnetic field strength. Next, go on with the next step. In the next step, you're going to find the force. So based on your force, motive force, where we're going to use these equations. Okay, and take note at the same time, we also in a different equation where we take note based on the length, if you still remember, where we have F equal to Ni. Okay, but at this point, we're going to substitute H with the length. Okay, so at this point, we have the value of the field is how much for the H, which is 10 for this value. Take note based on this value. Okay, you substitute here, after that times with the length, they give you the unit of the length. So go back the way, do they have the length here? Yes, they provide the informations for the length, which is 10 for 12 millimeter. So you substitute, you times with the value they given to you, 12 milli. Okay, so millimeter, just take the milli times, you get the last answer, which is 2387 ampere. Okay, so this is the one of the example concept. Okay, let's go on one more. This is should be the, okay, this one done. This is based on the turn coil. Let's see, they have one more now. Some is put as a homework. Okay, the one I put as homework, please do it. Okay, those done, just put it in a OneNote. Okay, even though sometimes we're not able to discuss during the class, but I always check OneNote. Sometimes I forget to put a remark that I already checked. Okay, so don't think that means not follow or monitor you. Okay, even though sometimes I know I liked it during the class, but I always have a look for each of the students based on the OneNote. So that's the way Miss will know whether you understand or not understand. Okay, so please take note, try to do. Okay, those can't paste it, just write in a piece of paper. So one day Miss will ask you, okay, maybe someone need to share to me right now based on the example that I given to you or as a homework. Okay, so that's the time you can send to me through the meeting chat. All right, so homework, when I have Miss highlighted homework, make sure you're done. Okay, no matter what, try to do it. Okay, so that's the one Miss want to explain. Okay. Next part here. Okay, this is the one. All right. Okay, actually, if you see this slide, actually should be at the before we go with the example. Okay, so just take note, this one will explain back, even though we did the example earlier. All right, so just have a look on this one. Okay, so have a look on this part. They have two image there. They given to you based on the one side of the image. They shows you have the materials here based on the iron, could be iron. Then they shows you in terms of the coil. Okay, the circle turn coils. And the next one, they shows you in terms of the short part. So what they mean, part means is like a way. Okay, we call as a part. Okay, so at the same time, you have a look. Sometimes they shows you in terms the way they build up. I'm not sure. Okay, do you see transformer? Okay, not the transformer, machine transformer. I'm talking about the transformer. Even we can build up the transformer. Okay, do you know that? I'm not sure, but we ourselves can build up the transformer based on the powers that we want. But usually they shows you in terms of okay, just give me 1 minute. Okay, you let me show you in terms of the image here whether I can find for you or not. Okay, not the movie, yeah. Yeah. Mm-hmm. Mm, Miss can't find it. Okay. This also we cannot see inside. Mm, okay. Maybe I shows you this one. Okay, actually this is the one we call as a transformer. So yeah, okay. So this transformer where we maybe how to say, okay, you may have a look. This is the one like a casing. Okay, they use like a casing. So by in terms of the casing, inside here they have like a square type, and each of the square, each of the square, they have the coils. Okay, so okay, transformer coil. Okay, it's look like this. Let's have a look. This is even this also they already okay, okay, so maybe this is the one they cover up like sellotape. Okay, actually they cover up with the sellotape. If you see, they cover up with the sellotape. At the inside here, you can see the coil actually. So they always have two sides of the coil. One in the right hand side, one is the left hand side. The way you build up the transformer. So when you have materials and you cover up, or we say as a not wrapped, which have like a coil. You round up your coil, your materials, okay, like a coil. So we have two sides. We have a left hand side, we have a right hand side. But this is the one just is our out view. This is just a overall of the view. At the same time, you may have a look. They have the package, not the package. They just have the casing. How they cover up the casing. Okay. Um, that's the one I want to choose to you, but I can't choose to you exactly the inside one. Okay. This is similar, but okay, you may have a look on this part also. But this is not the that one is want to let you all know. Okay, this but just a rough diagrams that you can have a look on this part here. Okay. Hmm. Okay, now mind. You will learn in a different module. Okay, so let's go on with our this one, our chapters here. Just continue back. Okay, so in terms of that, they shows you in terms of two image, okay, where we need to calculate based on the force equal to Ni. Okay, and this one, the A represented, they shows you a long part, the B, they shows you in the short part. Okay, what they try to let you know based in terms of the theory. So let me go with the theory part first here. So when they say magnetic field strength H equal to the measurements of the MMF, okay, per unit length of the circuit. At the same time, they also just let you know based on the currents they applied, okay, based on your figures. So it means figure 9 means is this one, the one they highlighted, figure 9 means is this one, overall of the figures here. And suppose we applied it based on the force, based on your current 600A to both circuits. Okay, how is it works? Okay, you need to calculate. At the same time, you need to take note based on the currents which is drive into your coil, okay, based on your part length. This one I call as a core. Okay, this core represent different material. Usually they can say it's iron. Okay, and where we need to know the length. How much is it the length? So in terms of your A, this shows you 0.6 meter. Okay, so at the B, you may have a look. Where this shows you 0.5. So that's the one they call. This one we call it as a short path. Okay, and the next one, the A1, they shows you a long path based on this one, based on the core, this core. Okay, so it's where they have two case. It's not two case. It means two condition. Okay, so two conditions. One is long, one is a short, and where they come out with the equation to be calculated. So this is the equation how they calculate. Again, based on the force divided by the length. At the same time, they also take note based on the numbers. Okay, sometimes they not let you know how much the value of the force. Okay, they ask us to find. So that's the time that you need to substitute based on the turns. This means how many turns that you have in a coil, then you times with the current, divide by the length. Usually the unit of the length they always provided to you. Unless they want to trick, okay, then they only give to you based on the force, based on your magnetic field. So that's the time you need to find how much the length. Okay, length means is the core. Okay. Okay, have a look on the next part here. Okay, based on your this part we call the relations between B and H. Okay, this is uh, how to say it's important for you to know. Okay, at the same time, they try to explain the relations between the B and age. What is it the B, what is it the age, and always they explain it based on the graph. Okay, the plotted graph. Okay, so let's see, let's go with this part here where they have based on the B. B, as we know, is a flux, okay, density flux, and at the same time we need to know we have the permittivity. So this is the one they call as permittivity times with the magnetic strength, okay, with the age. So just have a look. Later on, you may have a look on your points here based on the slides here. Okay. So just have a look on this part here based on this point 1, 2, 3, 4. Okay. The fourth point here where they specific based on the free space. Okay. Free space means is based on this one. As I informed to you, this is a constant value. Take note each of the constant value for you need to remember. Better for you to remember. Okay. So this is the absolute permittivity where they call as a free space. Okay, that's why I say they can say free space. Okay, free space. Second, they can say as a hair. Third, they can also say as a vacuum. Okay, so be careful when using these words here. All right. And the next one, you just have a look based on the relative. Okay, relative means based on the material. That's why we say the example we did only one questions we have go through based on the hair gap. Okay, based on the gap, they say as a hair material. Okay, not necessarily every time they give you hair free space. They can give you different material. So when they given to you different material, take note. You need to know what is it the materials, the value of the parameters value for the relative. Usually they will provide it to you how much the value. Okay, usually they will provide it to you. Okay, and the next one. Okay, this how we come out with the total of the permittivity, how we calculate it. So first they just wrote as a micro. The symbol is like a micro, but it's not micro. Okay, so which is equal to relative, which is equal to your absolute. So defined it based on the permittivity value. So have a look on the graph here. Okay, just take note based on this one. I want you to write down. Those have your notes with you, please write down. Those have notes with you, please write down. Okay, so the way they're using the equations here. Okay, so the first one B divided by the age where you had the permittivity absolute. The second one they're using the same one where when they defined it based on the relative, based on a different material. And the next one where they shows you based on a relative. How they get done? Usually they give you the value, but the way they specific for you this one, how they get the value of the relative is where they're using a flux density in the materials. Okay, divide by the flux density in a vacuum. Okay, so it's just for your information. This one just for your information. This one, please take note. I want you to take note. Okay, let's go on. Okay, just have a look on this part. This part look very simple. Okay, Miss let you know. Frankly to you, maybe it looks simple. Miss is only based on the VH curve here. Okay, this is the point they will trick you. Okay, let's see whether they have. Okay, this is a simple one. Okay, just have a look on this one first. Okay, maybe during the tutorials we do some questions, okay, based on BH curve. All right. So in this one, when they said BH curve, one based on your Y, this we call as a Y. Okay, so this is an X. So in terms of here, this is based on your flux, okay, density flux, and this is a field strength. Okay, the way they have the curve, just have a look each of the curve. They have difference, the specific based on the what type materials they're using here. What type material they're using here. Okay, they have steel, they also have fine, but in the steel they have two types different. Okay, but in our slide they only shows you right now only three types of material. Actually we have more than three types. Okay, but just for your slide, the one they just want to indicate we have three. So at this point, each of the curve, okay, remember not we plotted the graph this way, okay. They always give us, they provided for us the way they shows you based on the graph, the way they plotted. Okay, we're not going to do any linear graph. Okay, no. Okay, is this graph shape? They always is like a theory, but sometimes they ask you to plot the value. Okay, specific value. So example I said, okay, this you get your value here, then you get the next value here, this is the next value, then this is the next value. Okay, the first value is here. So that's the time they would ask you to plot it. Okay, but that's when they ask you to calculate one by one by one. Okay, so Usually this we not going to implement, okay, but this is where we always have based on your theory curve. Remember, this not we plotted, this is theory curve we have. Okay, let's go with the point here. So in terms of here, as I inform you, this is H, this is B. Okay, they give you based on the shield here, the based on the material. So you may have a look on the curve. Okay, example, this is a first curve. I just put number 1. I hope you can see this number 2. Okay, so this is number 2. This is the number 3. Okay, so at this point, they always ask you to specific. Okay, they always given to you. Okay, example, they can give you a B curve value. Okay, and mean they give you the B value is how much. At the same time, they can give you the H value is how much, and you need to find how much the B. Okay, example. Okay. Okay, so example, maybe I can give you the value. Okay, so I say the value of the strength, okay, based on the field strength, magnetic strength is which is stand for 300. So from 300, point out for me, okay, example, the type material I say is cascade iron. Okay, I just say as an iron material. And I please define for me, okay, determine for me, define for me, or show to me, okay, so based on the B value, based on the flux density value flux, okay. So from here, you need to define how much the value. So it looks simple. Okay, example, we said 3,000. So you just have a look on the 3,000 and you just have a look on the type of the material which I specific. So right now, I specific for you is the iron. So when I specific for the iron, you're going to have a look 300 at this point. So you're going to read your data, as in you're going to read your value for the B. Okay, for density, you just have a look at this point. Have a look at this point. Is how you read your graph as usual, how you read your graph. So at this point, okay, example this point. Okay, so maybe it could be 0.68 or can be 0.67. So this is the way that you need to specific. Example, may say it's 0.670. So this is the way you need to specific. All right. So this is just how you have a look on your graph, how you read your graph. It's look easy. All right. Okay. So the next one, just have a look, because from here later on, some of the questions they give you to find based on the magnetic strength, then they ask you to calculate based on your B, then after that they ask you to plot a graph, okay, or identify the value from the graph. All right, so as a way, as usual, how we plotted, this is quite easy, not quite easy, it's a simple. Okay, so have a look on the next one. This is one example. I think we only have one example. Yeah. Okay, maybe during the discussion, Ms. will provide one more example. Okay, so have a look on this part here. Okay, all right. So this one we have B equal to 1.70. Okay, based on the sheet steel layer, based on the H. Okay, they ask what's the value of the H here. What's the value of the H? Okay, they let you know based on the figure. It means this figure right now. Okay, they already let you know the B equal to 1.40 and continue cross until you encounter the curve of the materials, sheet steel materials here, and read the corresponding value of the H. So we need to know the value of the H, and based on the figure they given to you. So at this time, they already specific for you the B value how much. So they say is 1.7. So make sure when you want to specify based on the value of the H, it means it's going to touch based on the line here, the curve here. So it means as usual, you put a line here. Okay, so this is the one. It means the 1.4, the straight line touch the curve. Okay, so the curve, the one touching the curve, you read the value which is stand for your magnetic strength here. This one, this value. So from here you can define it. The value is 1000. It's very simple, as me said. Okay, but that's the one you will have a trick later on. Okay. This is a one of the examples here, the way they calculated. Okay, so you may have a look on the solutions how they calculated. Okay. Let's see. Okay, now this way, the way they calculated this one. Okay, just have a look. This is a figure, one of the figure where they specific for you the Ni, which is a 250, and determine the flux. So they ask you to define based on the flux, magnetic flux, not density, magnetic flux. Okay, and where the informations on this slide they given to you. the length equal to 0.2 meters. At the same time, they let you know the turn is how much, okay, and this is a core, okay, casted shield here. This is a core. This usually they say as a core, C-O-R-E, core. Okay, sometimes they specific for you what type of the material. So this is the type of material. Okay, type of material. Okay, and the next one, you may have a look. This shows you in terms of the cross section. This one, the cross sections of the square. Okay, the core. Right. At the same time, they let you know the flux. Okay, so it means based on this one, the length. Okay, based on the length is how much is 0.2 meter. So from here you can specify the value what you get for the magnetic flux. So the way they calculated, they defined it. Okay, H length equal to Ni, H length equal to the Ni. Then they just substitute the value directly to define the H value. So how they substitute? You may have a look here. When they come out Ni, okay, over length, this means this one 250 because they already specific for us 250. So you just substitute 250 divided by the length because the length, the value they given is 0.2 meter. So you just substitute 0.2 meter. Okay, then you can specify how much you get the value here. So once you calculate it, you can figure out the value of the flex here, how much. So they shows you 1.24. So from there you can specify how much the value for the next one. This is the B, the density. Okay, and now once they give you density, you can calculate based on the flux here, this one. AB flux equal to your BA, you just times with this one. Okay, so you can get the next answer based on this value. Okay, 1.24, how you get the value of 1.2. Based on the flux, okay, calculate times with the length. It means this one 0.01 meter. You get the last answer. All right. Okay, let's go on with the next one. Okay, next one is based on the electromagnetic induction. Actually, this is slightly related to your inductor part 2. Okay, is where they shows you based on the electrical inductions, the movements. All right. Okay, I just want to go directly to the law here. So just have a look. This law. Okay, have a look on the law. We call as a Faraday law and how they defined it based on the currents flow. So I think last time we have the right hand, if you remember. Okay, the way they grip, the cooper, the way they grip the cooper. Example, we say this is the one, I have the materials here right now. So example, I grab and I need to know the motions or the currents flow with the materials. Okay, so this is the one we call as a Faraday law. So just have a look on this one. Inducts, okay, EMF is set up whenever the magnetic field leaking, the circuit changes. So how is it works? So let me go with the point first, okay? The magnitude of the inductance EMF in any circle proportional to the rate of the change of the magnetic flux leaking the circuit. So now have a look on the diagram A, B, and C. The way it shows you. Have a look on the meter. Every time, okay, not every time. You have a look on the meter. Okay, this we call as a measurements meter, we call as a multimeter. Okay, sometimes they put directly what the meter is. Okay, so example, when you want to measure the magnetic field, so they're using a meter to check how much is it based on the flow. Okay, so in terms of the first part, they shows you they are connected to the positive, they connected to negative. Remember, any circuit when you are connected to your multimeter or you connected to your supply, we always have the positive, we always have the negative. Okay, the negative sounds as like a ground, the positive we say as a supply. Okay, but when based on your measurements, you always have two prob. We call this is a positive, this we specify as a negative, just to show the polarity, the flows, how is it works. So in terms of here, you can see based on the movements, how is it mentioned based on the movements of their motions. So that's the look this looks here. Okay, the symbol this shows you. It means you're going to have a flow from here, okay, and the currents from here, okay, based on your directions. At the same time, have a look on the B and have a look on the meter. Just have a look on the meter here. Okay, from 0, you're going to start to read your value. So of course, when we read any value, okay, example, this is a meter. So this is specific for you 0, and we always specific, okay, 1, specific 2, 3. At the same time, when you have a look on the side here, they have shows you in terms of what is the value, okay, in a minus form, okay. So in terms of that, you need to know how it works based on your flow currents. So the first one, they just specific for you is a 0, okay. So when when you have a current flow, okay, they shows you have a current flow into your materials part. Okay, you can see the meter, you can see the meter here. This one. Let's have a look on the meter here. Okay, so it's reading. You have some value. Okay, have a look on the B. At the B part here, they shows you 0. So we don't have any, how to say, we don't have any currents or magnetic field into your materials part here. So when we say it's a 0, so it looks like we say at the release part. They in the conditions of the release part. So when you have a look on the C, you can see the way the moments, the motions, or we say the movement, is be in the different directions when we go to the different reading, because we always read our things in terms of the clockwise in this way. Okay, but when you see the knee from 0 going to the next side, it means they're going to be in the opposite directions. So that's the one you can see the flow. The first one they follow on this part, the second one they're going on the different directions. This is the one we call as a Faraday law. But okay, most of the thing is related to your EMF based on the magnetic, how the movements happen. Okay, so that is the one that you can see here. Okay, even though besides that it shows you in terms of the hand. Okay, those want to try, you may try right now. Okay, you have the point out as your hand here, your thumb as a motion, the first finger, this one as a magnetic field. Okay, and the next one as inductive EMF, the way of the movements, how is it happens. Okay, and based on your diagrams, okay, you may have a look on this one later on. Okay, based on the way they increased the flux. Okay, at the same time we have this increase the flux. How is it works? So when you say you want to increase the flux at the loop point, okay, you can see the direction we call as a velocity. The symbols like they defined it at the as a v, we call as a velocity. Yeah? So this point we say it's a right motions moments, so it's going to increase. Unless it's opposite direction, they're going to see this increase. That's the one we have happens here at the A. What happened at the C? The B is just a release. The mode are in the they don't have any how say any movements. Okay, they have no any movement. They in the steady state where we call as a release state. All right. So that's the one. Okay. So all right. Okay, this is a Fresnel law. Just take note. It's the same thing concept, but one they shows you in terms of these directions. Okay, based on the multimeter. One they shows you in terms of the finger. Okay, I think last time we have the right hand grip, if you still remember. Okay. All right, so this is the one. Okay, next part will be your second sections. Okay, before that, okay, if you have time, not have time, I want you to have a look on the first question that we have. We don't have much on it. Okay, example, the units where you're using for your magnetic flux density. Okay, okay, this one you already have the answers. Make sure you calculate it to define it based on the units here. Okay, cross sections, how you calculate it. Okay. And the next one, they also have based on the calculations. Please, I want you to try, okay? Please want you to try. This is the next question. Do some calculations. All right. And the next one is just a line and match. Okay. So what is it they call as a currents? Which one they measure based on the electrical quantity? Okay. So these are one of you can say. One is based on the magnet bar, how it works based on the arrangements, based on the knot pole. Okay, the arrangements knot pole. Which time we have the attractions happen, which time we have reflections happen. Reflections means they move away, okay, move far away. Attract means they come closer. Okay, so that's the one we have the concepts here based on your two magnet bar, right? Okay, you may have a look later on. Okay, this is something in your slides. Okay, quick review questions. You can have a look, you can answer here later on. Okay, all right. So for these sections, I will stop here. I just want to continue with the next part, but we just take a break before we go on with the next part. But next part, just take note, we have some introductions. We don't have any calculations part. Okay, most of the things will cover up on your tutorials or discussions calculations. Okay, based on the section. Okay, we just stop here for today for these sections.